Hello, in this video we're going to look at some curve sketching. Now curve sketching is quite fun, but it's also quite involved because it kind of ties together a lot of the concepts that we've had from the whole course so far, limits, differentiating, all this kind of stuff. While it's definitely true we could just put an equation like this one here into a computer and get it to draw a picture for us, going through the exercise of manually figuring out how much of the picture we can sketch ourselves helps us to really solidify our knowledge, so it is a worthwhile exercise. So what I'll do is I'll go through the kind of checklist of steps that is in the Stewart textbook, where we go through these various things, find them, and then at the end we put it all together and draw our picture. I'll go through them step by step, and I'll probably chapter the video as well, so you can jump through any particular place you want. Alright, I guess without any further ado, let's get to it. So, here's our function, y equals x cubed over 3x plus 1. Let's start from the beginning. So we'll start with the domain. Right, so the domain, so that's our step A in the checklist. The domain is not specified, so that means we just look for basically as many numbers as can go into a function as possible, and basically anything is fine except when the bottom of that fraction is going to be 0. So our domain is going to be all of the real numbers except for when 3x plus 1 is 0. So we could write this as 3x plus 1 not equal to 0, which means that x is not equal to negative a third. Otherwise, any value of x is fine. We will expect there's probably going to be an asymptote at negative a third, but we'll get to that in a minute. Okay, step B, which is the intercepts. In fact, what I might do is I might just jump between pages, and I'll do my working on a separate page, and then come back and put the information here. So our intercepts are going to be basically when the y-intercept is when x equals 0. So we'll have y equals, remember our function is y equals x cubed over 3x plus 1. If we make x equals 0, that tells us that y equals 0. So our y-intercept is going to be at y equals 0. Maybe I'll hide that so I can come back to it easily. And then my x-intercept, well, and then maybe multiple, that is when y equals 0. So this means we'd have 0 is equal to x cubed over 3x plus 1. The only way that can be 0 is if the top of the fraction is 0. So this implies x cubed is 0, and the only way x cubed can be 0 is if x is 0. So the only x-intercept is x equals 0. So let's transfer that back to the other page. So our y-intercept y equals 0 is our y-intercept, and our x-intercept. Okay, and so those points are just 0, 0 in both cases. They're the only intercept in our graph. Okay, that brings us back to our checklist as well. Next thing we want to think about is symmetry. Now, some graphs are going to have some really obvious symmetry in them, if it's like an even function or an odd function, or maybe we've got something periodic going on because we've got some trig functions. But nothing is obviously symmetrical about this one, so we're just going to say no to that. I mean, even if there was, it would show up eventually, but there's nothing obviously symmetrical about this that we can take advantage of to save us some work. All right, next up is asymptotes. So let's do the asymptotes next. Our asymptotes are when we have basically a value at the bottom of the fraction going towards 0 in this case. So I'll jump back to my working screen. We're going to have a vertical at x equals negative 1/3 because the top of the fraction, if we just look at our fraction for a second, the limit as we go towards negative a third here, well, the numerator x cubed, that's not going to be 0. There's not going to be any sort of L'Hopital's rule style cancellation here. So x to the 3 is going to go to a number, negative a third cubed. 3x plus 1 is going to go to 0, and so we're going to have a vertical asymptote. We do also need to decide what the asymptote is going to look like. So it's going to be, well, it's going to be vertical, but we don't know if it's going to look like this, or maybe it looks like this. We need to figure that out by taking one-sided limits to get that right. Okay, so let's take one-sided limits of this function as we approach negative a third from either side. So we'll start with the limit as x goes to negative 1/3 from the left, so from a more negative direction, of x cubed over 3x plus 1. Okay, so let's just have a look at what's going on here. The top of the fraction, that is going to go to a negative number. If we just think about what the overall behavior of this piece is going to be, it's going to go to negative 1/3 cubed, which is just a negative number. If we then look at the bottom of the fraction, well, we know it's going to go to 0 overall. If we look at this piece, 3 times x, what's that going to be? What we really want to decide here is whether the bottom of our fraction is going to be positive or negative. So we know 3 times negative a third is negative 1. That's no surprise. If x is slightly more negative than that, so let's imagine x is, for example, negative a half, which is more negative than negative a third. Then we'd get 3 times negative a half, which is negative 1.5, plus 1 would give us negative 0.5. So what we find is that this here, that 3x term, is going to be less than negative 1 if x is coming in from the left-hand side from a more negative value, which means that overall the bottom of our fraction is going to be a number that's going to be slightly negative, because the first part is less than negative 1. Add 1 to that, we're still in the negative territory. So this is going to be small negative number. So that limit is overall going to be negative something over a tiny negative number, which gives us positive infinity, negative over a negative. We can do the same exercise as x goes to negative 1/3 from the right of the same function. And once again, we just talked about this, at the top goes to a negative number. This time, if x is coming in from the right-hand side, imagine your number line, here's negative a third. Now we're taking a value here which is slightly closer towards 0. Then what we're going to get is that this term here is going to be slightly bigger than negative 1, slightly more positive, sorry, than negative 1. And so overall, when we add these together, we're going to get a positive, small positive number. If you're really unsure about how to think about this and you're a bit stuck, one thing you could do is you could actually pull out your calculator and just put in a value that's close to negative a third but slightly larger, and then see what kind of values you get out of your calculator if you put them into this function. And what you should find in this case is that the closer you get to negative a third from the positive side, from this side here, the bigger the positive number, the negative number you get. So this one is going to be a negative thing on top divided by a tiny positive thing, which overall will tend to negative infinity as we get closer and closer to negative a third. So that means that our asymptote is going to look like, this is, in fact, let's put on this picture here, something like, let's see, so it goes positive infinity when we're coming in from the left, and so our asymptote is going to look something like positive on the left, and on the right it goes to negative infinity. So it's one of these kind of asymptotes. So we need to include that in our picture when we eventually get there. All right, how are we going to summarize that for our other page? We'll maybe just draw that little sketch. It's one of these types. We can figure that out when we get to drawing the graph a bit later. All right, next up is increasing versus decreasing. All right, so now we're going to get into the realms of having to differentiate this thing. To figure out if something is increasing or decreasing, we calculate its first derivative and then we look to see whether that's positive or negative. So let's get differentiating. So our function is I'll call it f of x now, because our function is y equals f of x is equal to x cubed over 3x plus 1. And now's the part where we've just got to be a little bit careful, because it's quite easy to make mistakes when we're going through all this derivative stuff. So our first derivative is going to be, now this is going to be a quotient rule because we've got a fraction, and we remember our quotient rule says that if we've got two things like this, the derivative's f prime g minus fg prime all over g squared. So my derivative will be f prime 3x squared times g, 3x plus 1, minus f x cubed g prime, which is 3, all divided by g squared, 3x plus 1 squared. And if I just tidy this up a little bit, I'm going to have overall 6x cubed, if I just expand everything out, 6x on the top that is, leave the bottom factorized, 6x cubed plus 3x squared over 3x plus 1 squared, and then I've got a common factor of 3x squared on the top there, so I can then refactorize this, which will help me to make signs decisions. 3x squared times 2x plus 1 all divided by 3x plus 1 squared. All right, what can we say about this? Well, first thing we might do is we might just have a look and see if there's anything that's obviously positive, because if something's positive no matter what value x is, then we can kind of ignore it when we're trying to decide whether this thing is positive or negative. So I can see that this thing here, that's positive no matter what happens. And in a similar vein, so basically anything squared, so likewise this term here, that's also positive. So the sign of my first derivative just depends on the sign of this 2x plus 1 term. So f prime of x is therefore greater than 0 if 2x plus 1 is greater than 0, or if we rearrange that, that says x is greater than negative 1/2. And similarly, f prime of x equals 0, well that's only true if 2x plus 1 equals 0, which means that x is equal to negative 1/2. That's going to be our critical point. Looks like it's the only one we've got in this problem. And then for the increasing parts, f prime of x is, decreasing, less than 0 if 2x plus 1 is less than 0, which means x is less than negative 1/2. All right, so let's just go and transfer that knowledge back to our original picture. If I go back here, let's also maybe just keep track of what's going on with our x's now. So we know that we've got, here's our number line, here's 0, oops, cancel that. Here's our number line, here's 0 just here. We know we've got an asymptote at negative a third. Yeah, so we've got this vertical asymptote going on here. And now we've also got this other point of interest, which is a critical point at negative 1/2. So f prime of x, if we were to sort of split this up, so when we're looking at the various intervals, we need to consider that negative 1/2 value, which is where it changed, and we also need to think about our asymptote because that's going to be relevant. So f prime of x, if we look at the sign of this, so I'll kind of split it up into these various parts. So in this region, we decided it was decreasing, less than 0. In this region, we decided it was increasing because whenever x was greater than negative a half, it was positive. And likewise, for the rest of the picture, it's also going to be positive. In fact, sometimes we like to just draw a sort of upwards arrow just to indicate what's going on. And then it was decreasing for this part. And then at negative a half, our derivative was flat. So we could kind of indicate it like that. All right, and if we wanted to do this in terms of writing down intervals, we could just write that in interval form. So we can say it's increasing between negative a half and negative a third, and also between negative a third and positive infinity. Remembering there's an asymptote in the middle there, splitting those two intervals up, and it's decreasing on negative infinity through to negative a third. All right, we're getting there. Local max and min, I'm just going to put that one straight in. If we look at what we've just come up with here, the only possible local maximum or minimum could be at negative a half. That was this point where basically it went from decreasing to increasing, and it stopped in the middle, and you can just see by thinking about those signs that this must be a local minimum. There are no others because there are no other points where f prime of x is equal to 0. So local min at x equals negative 1/2. Okay, now for the bit that I don't like, which is the concavity, because we're going to have to differentiate this again, because this is all to do with second derivatives. So concavity, points of inflection, jump back to our working page and see how we go with that. Right, let's have a look. Concavity involves f double prime of x. So we're going to need to calculate that before we go any further. So let's just yoink our f prime of x working, because we're going to need that. I'll just copy paste this back to here. I might just rub out my highlighting as well. Okay, so that's my f prime. In terms of which one to work on, because we've got a couple of different forms, it's probably easiest to work on the factorized form, but we're going to do a little bit of work before we're done. So just roll up our sleeves, literally, and see what happens if we try and differentiate this again. So I'm going to focus my attention, in fact, let's just rub out the intervening bits. Bye-bye, bye-bye, I don't want you. Let's just put this over here. That can be our f prime formula, and so f double prime of x, let's see how we do. So f double prime, it's quotient rule again. This time the quotient rule is a little bit more complicated because we've got a product on top, so we're just going to have to be very systematic. So first thing is going to be f prime g, that's the top thing differentiated, which is going to itself be a product. So let's put that in the square brackets for differentiating the numerator. So it's a product itself, so it's going to be derivative of the first thing times the second thing, plus the first thing, 3x squared, times derivative of the second thing, which is just 2, times, that's my derivative of the top, times the bottom, 3x plus 1 squared, minus, let's see, we're going to have top thing, 3x squared, 2x plus 1, times the derivative of the bottom thing. Now that itself is going to be a chain rule, so it's going to be 2 times 3x plus 1, then times 3, which is the derivative of the inside. And all that gets divided by 3x plus 1 to the 4. Okay, now the good news is, once we're really happy with differentiating and doing these kind of things, computers are much better at doing it for us. So in the future, once we're very confident that we know how this works, you don't really need to feel too guilty about using a computer to do this kind of derivative for you. But we're going to do it the hard way. Kind of satisfying anyway if we just don't rush it. So that's going to give us, let's see. Okay, first thing I can see here, I can see that I have a 3x plus 1 here, and also here, and also here. So I can actually just cancel off one of the 3x plus 1s right out of the gate before I do anything. So I'm going to kill that one, turn that into a 1, and turn that into a 3. Just as like a quick simplification that I can see before I do too much work on this. So let's see. And I'm going to have to pretty much expand everything out because ultimately what I want to do is factorize the top into a number of products. If possible. It might not be possible, who knows, we'll find out. Bottom can stay as it is because it's already in a nice factorized form. Okay, so on top we're going to have, let's see, that square bracket is going to become 12x squared plus another 6x squared. That's 18x squared. And then plus 6x. And that's times 3x plus 1. We got rid of one of those. That's cool. And then, let's see, the next piece. Okay, the 2 and the 3, that's just, it makes a 6. 3x plus 1's gone. So the overall factor is going to be 18, since it's 18. And then I'll put the x squared inside that bracket. So it's going to be 18 times 2x squared yes, that's right, 2x squared plus, no, sorry, try that again. Let's keep the x squared outside of the bracket. I don't know why we're doing that. That's just crazy. 2x plus 1. All right, and then divided by the same denominator, 3x plus 1 cubed. Right, let's see what we've got now. Okay, I can see that we have, on the top, we've got 3 lots of 18x. Oh, this is a dog's breakfast, isn't it? We've got a common factor of 18, of 6. Okay, let's just, we can do this. Right, so we've got 18x squared. Oh, who cares? Let's just expand it all out. 18x squared times 3x plus 18x squared. If in doubt, expand it out. Plus 18x squared again. Both of those terms are 18x squareds. Plus 6x minus 36x cubed minus 18x squared, all divided by same thing. Right, I can cancel off that one and that one. So x squareds, it looks like I've got 36 of them. No, I've got 18x squareds only. That's this term here. Let's start with x cubed, shall we? So we've got 3 18s, which is 54 x cubes there, minus 36 of them. Sounds like 18x cubed total. Now let's look at the x squareds. We've got plus 18x squared. And then we've got, how many x's have we got? Plus 9x. This is now not looking so terrible anymore. All divided by 3x plus 1 cubed. Okay, I've got a common factor of 9x that I can take out the front on top there. So now I'm trying to factorize the top. So it's going to be 9x times, let's see, 2x cubed plus 2x plus 1. All divided by 3x plus 1, all cubed. Okay, I don't think we can really take this any further. That should be an x squared, not an x cubed. Just double checking my working to check I haven't messed anything up, but I think that's right. Yep. All right, so what can we do with this? Remember, what we're trying to do here is just decide whether it's positive or negative. I'm going to look at this quadratic term first. Let's just have a think about it for a second. That's this one here. Does this quadratic change sign at all? Well, remember if we've got a quadratic ax squared plus bx plus c equals 0, which may or may not cut through the axis, and it may or may not be like that, or whatever. But we know that if the discriminant b squared minus 4ac is less than 0, then we have no roots, which means the whole thing is always positive or always negative. It never crosses the axis. All right, so for our particular example, b is 2, so b squared is going to be 4. 4ac is going to be 4 times 2 times 1 is going to be negative 4 overall. And so actually, and if we just put in a test value like 0, you can see that that quadratic is going to be positive. So actually it turns out this quadratic is always greater than 0. All right, so now to look at the intervals here. Got our fraction, we know that that quadratic piece is always positive, so the sign of f double prime of x is just going to depend on the signs of these other two pieces, the 9x and the 3x plus 1 cubed. Okay, so let's just think about that for a sec. We know that 9x is greater than 0 when x is greater than 0. And we know that 9x is less than 0 when x is less than 0. Okay, a little bit of rocket science there. And then on the bottom, 3x plus 1 cubed is greater than 0 when x plus 1 cubed is greater than, well, it's when 3x plus 1, sorry. Basically, cube in terms of sign behaves the same way as x itself. Because remember, if we've got a graph of y equals x, looks like that, x cubed just looks kind of like that. So the signs are the same. So when 3x plus 1 greater than 0, which means x is greater than negative 1/3. This is that same asymptote value we had before. Okay, so cool. And then it's less than 0 when similarly x is less than negative 1/3. And it's those two terms that are going to determine the overall sign of our second derivative. So there are two kind of threshold values. There's one at 0 and one at negative 1/3. So if we look at negative 1/3 here, 0 here, and look at what's going on with our signs. So maybe if I just change my highlighting to be green on the bottom. So in the first region, when we're less than negative 1/3, we know that our term on the bottom is going to be negative. So let's just put a negative here. So what we're going to do is we're just going to form that overall expression. We know this quadratic piece is always positive, and no, sorry, I should have made that green. So 3x plus 1 piece is going to be negative, and then the 9x piece is also going to be negative. And so overall, we're going to have a positive f double prime when we're to the left of negative 1/3. When we cross that negative 1/3 boundary, our 3x plus 1 term is going to become positive from this bit here. So if we look at our expression, the 9x is still negative. The quadratic is always positive, we figured that out. And then on the bottom, this piece is now going to be negative. And so overall, our f prime is therefore going to be a negative over a negative, which is actually, what am I saying? I said something wrong there. Oh yeah, this one on the bottom became positive. Try that again. It's going to be negative over a positive, which overall is going to be a negative value. And then, once we cross 0, then the 9x piece also becomes positive. And so our fraction becomes a positive times a positive divided by a positive. And so overall, we have a positive value. Right, so we can summarize that by saying it's concave up, which means f double prime is greater than 0. The intervals where it's concave up is negative infinity up to negative 1/3. and 0 up to positive infinity. Concave down, which means our second derivative negative. That's in between negative a third and 0. And then point of inflection, that's when it changes concavity from positive to negative. Now, the asymptote doesn't count because the function isn't continuous through there. So the only point of inflection is when we transition from this negative curvature to this positive one. So at x equals 0. And let's just remember what concave up and concave down mean. Concave up just means that our graph is curved upwards, or it's a happy graph because it looks like a smiley face. Concave down means our graph is curved downwards, so it's a sad graph, or a sad face. Okay, so let's transfer that information back to our summary page. So we have that it's concave up, negative infinity to negative a third, and 0 to infinity. So let's just go back up here. And then 0 to infinity. And concave down in between those 2 points, and then inflection at x equals 0. Okay, so we can kind of add this, I guess we can sort of add this to this little summary here as well. Concave up, so that means it's going to be kind of upwards curving between negative infinity and negative a third, so it's going to be kind of upwards curving like that. And we know it's going to go, so it's going to be that kind of shape in that region. We know it's going to, there's an asymptote there, and then it has to be concave down up until 0. And then at 0, it's going to change and become concave up again. So it's going to look something like that as it crosses those boundaries. We'll figure out the details when we get there, but we're getting close. All right, so in fact, we've pretty much got everything now. So now we're in a position where we can assemble it all together and with a bit of luck, produce a graph. So the working was kind of horrible, especially when it got to the concavity part of it. But we have kind of summarized everything now. So now it just remains to try and draw a graph of this thing. Right, so what I'm going to do is I'm going to sketch some axes and then we'll see if we can just add the information onto it. Now it's just a sketch. It's not going to be perfect. I'm not going to really try and figure out any particular values of anything. All the action, let's make that horizontal, that's not very good. Not very good at all. Let's go for a nice horizontal line. That's better. Use the ruler. Much better. Okay, we know that all the action happens around 0. There was some stuff happening around about negative a third. And then we also found there was a local minimum somewhere that I've forgotten. So let's just go and have a look at that. Negative a half. Okay, so negative a half is, in fact, maybe let's move this slightly. Let's make that one negative a half instead. That's where our minimum is. And then there was also a asymptote at negative a third. So let's draw on the asymptote. That one's easy. We also know there were no horizontal asymptotes, so we're not going to bother trying to draw them on. Right, now we just need to make sense of all the information that we've got and see if we can apply them to that graph. Okay, so that was our asymptotes. Intercepts, that's easy. We know that the graph goes through 0, 0. The x-intercept and the y-intercept are actually the same point and they're just here. Okay, so that's really all there is to it. With that one, we know our graph goes through that point, so let's just put a nice big point on there. Nice. Okay, then it has to be increasing and decreasing. Oh, local minimum at x equals negative a half. Okay, we know that it's concave up, and as we go to negative infinity, oh, we didn't even write this on here, did we? When we did the asymptotes, we found out that f of x goes to infinity as x goes to negative infinity and infinity. We found out that basically our graph, if we take the limit as x goes either way, it ends up just being infinity. So it starts. So basically, because there are no other x-intercepts of any sort, it can't be that our graph started at negative infinity and came down across the axis because we didn't find any other x-intercepts. So what must have happened is that that local minimum we found at negative a half, just going back, see we have a minimum at negative a half, must be somewhere above the x-axis. And we also know in terms of the asymptote that it's one where it is going, it's going up towards it. So the only information that really makes sense, and we know that we're concave up, the only sort of thing that could possibly be happening in this area is that our graph comes in from infinity, gets to this point as a local minimum, turns around, and then shoots off to positive infinity along that asymptote. Okay, so maybe we'll just extend this out slightly further. And okay, because concavity has to be positive, it has to be curved upwards the whole way through. Our graph is curved upwards the whole way through. It's going off to the asymptote, which is good. It has the local minimum at negative a half, which is good. And it has the decreasing up to negative a half, negative a third, and I've done that wrong. I just transferred that information incorrectly, I just realized. We did it right on the other page, we just did it wrong here. And it's increasing from negative a half to negative a third. That's better. Okay, so it's decreasing up to negative a half, and then increasing up to a negative a third. That's good. All right, we now know that concavity-wise, we know that our graph has to be increasing between negative a half and negative a third. Done that. Now we're between negative a third and infinity. We're going to be increasing the rest of the way. Okay, so that's good. We're coming up from negative infinity. So we know it's something like this. We know it goes through this point. The only thing we need to really think about is when it's going to change its curvature. If that were the case, it would be negative curvature, like curved downwards the whole way. But we need to, it actually changes at 0, I think we said. Yes, so it changes to being positive curvature, or curved up, when we get as far as this point here at x equals 0. From 0 infinity, it's curved upwards, but up until 0, it's curved downwards. So what must actually be happening is we take a picture. The asymptote means it comes from there. It's concave down, but it's increasing, so it looks like this. Gets to this point, and then... Oh, we've actually missed something. I just realized. When we were doing the local minimum and maximum, if prime of x is also equal to 0, I just made a mistake there. Also, if x equals 0. This can also be equal to 0 at this point here. Okay, so there's an next piece of information that I forgot to do before. We'll just add that in. Right, where are we? Local minimum x equals 0 and flat. Okay, it's not a minimum or a maximum because it's increasing on both sides, but it is flat at that point. So we should actually include that information in our picture. So that means rather than going through like this one, like a cubic or a tangent curve, it's going to come into that flat. So we've finally got everything we need. It kind of comes in flat here. And then it's concave up and increasing for the rest of the picture. So off it goes. Just emphasize the flatness. There we go, that's better. And that's going to head off to infinity. So that is a pretty good guess about what our function y equals x cubed over 3x plus 1 looks like. Okay, and in fact we might just jump across the computer and see if we can plot it and see how close we were. So what I might do is just open Desmos, is nice for plotting graphs. Graphing calculator. Here it goes. So what was our function? Was y equals x cubed all divided by 3x plus 1. Look at that. That's very similar to what we came up with, especially if we zoom in a wee bit. Okay, so you can see, very much like what we have decreasing, local minimum, increasing, asymptote, increasing, comes through flat, concave down, point of inflection, now concave up, increasing. So our picture that we came up with, I think, was a pretty good demonstration of that. So there it goes. I think we captured the shape pretty darn well. So we'll call it quits there, and we'll see you next time. See you later.